In 1887, Heinrich Hertz was busy confirming Maxwell's theory of electromagnetism. He did an experiment that showed a link between light and electricity, but offered no theory and basically appears to have moved on. 12 years later, in 1899, Thomson demonstrated photoemission using UV light. That seems to have just been a demo, so it took another 3 years until Philip Lenard produced some data, inventing the stopping potential experiment that you may get to see in class. Another 2 years after that, in 1905, Einstein released his theory of quanta of light, which included his incredible equation that won him his Nobel Prize for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. This was not E equals mc squared, but what I consider to be the most wonderful equation, E equals hf. Today's lesson video looks back to those experiments, the ones that discovered new behaviours that would cause great arguments amongst the greatest of scientific minds. So, what exactly is the photoelectric effect? This is a piece of zinc sitting on a gold leaf electroscope. We'll give it some charge, and as expected, the gold leaf rises because like poles repel. So far, so IGCSE. The interesting bit is that if I bring a UV light over here, the gold leaf falls. Clearly it's losing its charge. The UV light has caused the gold leaf to lose its charge, which means that UV light is causing a current. UV light is causing a current. Now that might not be too surprising, but here's the fascinating bit. Let's do the same thing. Zinc, gold leaf, charged up. This time I'm going to put a red light above and nothing happens. To get really interesting, let's increase the brightness. Still nothing. In fact, no amount of red light will get the current to flow. Not even a laser. But a tiny blue light will. That's photoelectric emission. Electrons can be emitted from a metal surface when it is illuminated by electromagnetic radiation. But not just any kind of electromagnetic radiation. The scientists did some experiments 100 years ago and made some observations. Right, so let's put aside theories for now and focus on observations like a good practical physicist should. Let's list out the observations that were made. Light incident on a clean metal surface can eject electrons from the surface. Okay, so this is the starting point. Shine a light on a piece of metal and electrons can be ejected. Not just moving around a bit, they are brought to the surface and leave the surface. Ejected. The kinetic energies of the photoelectrons are independent of the intensity of the incident light. So, electrons are ejected and fly off with speed v and kinetic energy Ek. The brightness does not affect Ek. That's what the scientists observed. The maximum kinetic energy of the photoelectrons depends only on the frequency f of the light for a given material. Right, so similar to the last one, but a little bit different, a little bit deeper here. If the frequency of the incident light is too small, 0 electrons are ejected from the emitter electrode, no matter how large the intensity of the incident light. This is what we saw earlier, with the UV light discharging the electroscope, but the red light failing. When photoelectrons are emitted from the emitter electrode, their number is proportional to the intensity of the light, hence maximum photocurrent is proportional to the light intensity. All that's saying is a brighter light increases the current. Photoelectrons are emitted almost instantly, less than 3 nanoseconds, following the illumination of the emitter electrode, and this time is independent of the intensity of the light. So, those were the observations, but next we need to understand why Einstein needed Nobel Prize level thinking to explain these explanations. Their observations came first and upset everyone, so let's see why. I'm going to go back through these and see how classical theories stand up. Today I'm looking at how wave theory stands up to these observations, but back then there was no particle theory, no wave theory. There was just theory, a single classical theory that was about to fail. First off, light incident on a clean metal surface can eject electrons from the surface. Well, classical theory actually starts off well here, because this is okay. Shining a wave onto a metal can provide energy, and if electrons absorb that energy, then they could, in theory, be ejected. Okay, alright so far. The second one then, the kinetic energies of the photoelectrons are independent of the intensity of the incident light. This is the first fail. If waves are emitting electrons, then having a more intense wave should give the electrons more energy, so they should fly off with more kinetic energy. This was not observed. Next we have the maximum kinetic energy of the photoelectrons depends only on the frequency f of the light for a given material. Well, actually this relates to the last one. Classical wave theory says the maximum kinetic energy will depend on the intensity, so it doesn't depend only on the frequency. Okay, fourth. If the frequency of the incident light is too small, 0 electrons are ejected from the emitter electrode, no matter how large the intensity of the incident light. For this one, wave theory is a total utter fail. In wave theory, frequency is just telling us how close the peaks are to one another. It's not the energy or anything to do with the energy, just how close the peaks are. So I can't imagine at all how the frequency could control whether photoemission happens or not. It just doesn't make any sense. Fifth, we have when photoelectrons are emitted from the emitter electrode, their number is proportional to the intensity of the light, hence maximum photocurrent is proportional to the light intensity. Alright, back to form for the classical theory, as it does explain this one just fine. A higher intensity wave has more energy, so it should be able to emit more electrons each second. So the current can increase. That one's okay. Lastly, photoelectrons are emitted almost instantly, following the illumination of the emitter electrode, and this time is independent of the intensity of the light. Now this is a curious one. Needing time to emit the electron is fine, since the wave might need time to transfer sufficient energy. But if that is the case, a low intensity wave should be able to emit electrons, just needing more time to transfer the energy. The observation, however, was that the emission was delayed slightly, but by the same time, no matter what the intensity. Well, 6 observations, and 4 of them can't be explained by the current classical theory of the time, which we now think of as wave theory. Time for something new. And to learn more about that, have a look at the next lesson video.